last time we had looked at convective diffusion, which is diffusion from flowing fluids to intercepting objects, and the objects, the most ideal objects of course are right cylinders and right spheres. We had looked at right cylinders and then had come up with theoretical expressions that allowed us to relate it to either particle diffusivity through what we call the particle Peclet number, and to a certain interception parameter where you do not have particles that are diffusive, but really riding the streamline and getting collected. Now, let us take another case where this is called diffusion from pipe flow, and the reason to consider this, it is quite different from the pipe flow that we think about in chemical engineering, in that when we have pipes that are, you know, very small in diameter and large in length. So, you have, you know, the Z dimension being really large and the diameter, whatever it is, which can be called, we were calling in this case we can call it, I think, dP, is very small. Then what we are interested here, so here we are calling the radius capital R, so we can just use that. So, if we were to look at an enlarged version of this, right, what we are looking at is that there is a pipe with radius R, and this dimension is going to be long, and as the aerosol laden flow is coming in, you are going to have particles starting to diffuse in the radial direction. So, you have diffusion in the radial direction. And the question that we are interested in answering is that will a particle have enough time and diffuse to the wall and get deposited on the wall by the time the fluid flows all the way through the pipe? That is really what we are interested in. And over here what is being shown, of course, is that you can have both laminar as well as turbulent flow. And for the laminar flow case, of course, we have this, you know, laminar velocity profile, and we will write the equation in terms of that. And we have this other understanding that within something like, and notice this is very small diameters. So, you have maybe a diameter of the pipe and you have a radius of the pipe. Like within about 40 diameters of the pipe, and then still we will notice that there is going to be a long length of the pipe still remaining, right. You would have fully developed velocity profile, which is sort of something that we all use as a general, you know, thumb rule. So, what do we have? We have this idea that the particle diameter is much, much smaller than this tube diameter, which is equal to twice the tube radius, which we are calling capital R over here, right. We have fully developed flow, and we just go ahead and write the equation as U del N by del Z. You have the particle number concentration decreasing as you keep going down this, and the particles are diffusing in the radial direction. So, you have a 1 by R del by del R of R del N by del R, right. And then we have Also the which is in this case sort of an axial diffusion, which we will say that that can be neglected. And of course, we recognize that this u can be written in terms of an average velocity as we are used to writing it for fully developed laminar flow, 1 minus r by r whole square, to just give you the equation. And our boundary conditions here are that the particle concentration is really constant across the tube inlet, right? That is the way we conceptualize it. So, the boundary conditions then at z equal to 0, we have n is equal to some initial concentration. We can write it as n naught, sometimes we have written it as n infinity, for all r away from the wall, right? The moment you step slightly away from the wall, you have a constant concentration, and that at the wall, you have a perfect sink. So, you will have 0 concentration. So, these are our conditions, and we have this idea that for Peclet number greater than 100, right. So, here we have, as we said, particle diffusion in the radial direction and flow in the axial direction. So, where you have large Peclet numbers, you are saying that your right, this is where you have greater Peclet numbers, you are basically saying that you can neglect diffusion in the axial direction. So, you can neglect in that it's just the flow that's going to carry the particles, right. So, then with this kind of idea, we have an analytical solution. We will just take a look at the form of the solution. We have these kind of solutions that are standard solutions over here, and you have a parameter which actually what I miss saying over here is that we can non-dimensionalize this equation. So, we can non-dimensionalize this equation in terms of a non-dimensional radial parameter rho and a mu, as it's called over here, and in some cases books they write this mu as a pi, but it is the non-dimensionalization is in terms of this parameter mu, which is in terms of pi d z, which at the end of the pipe is nothing but the entire L. So, I mean when you finally do the integration, this will become a pi d L by Q. This Q is nothing but the flow rate in meter cube per second, and the flow rate is nothing but a pi r square into this UAV, right. So, with that non-dimensionalization, we are able to go forward with the solution, and you can see that the original reference, you can go and get it if you like and take a look at it. So, it gives you these solutions in terms of a penetration fraction, right, which is what fraction of particles escaped the deposition and got out of the pipe. But what is being plotted here is a 1 minus p, which is what is the fraction of the particles that actually deposited within the pipe, right, and as a function of that mu, which is the pi dl by q parameter. And so, the solution then pretty much involves, even though we write it for smaller than 0.02 and greater than 0.02, you can of course notice that where you have 0.02, you are going to really have very small amounts of deposition, right. You are going to really have just 10% deposition or so when you have these small values of mu, and only as you get to large values of mu, you will start having fairly significant deposition. So, for all practical purposes, here you are going to be using the mu greater than 0.02 case, right. Where is the application for this? If you take a look at the Hind's book, there are things called diffusion batteries. So, diffusion batteries might have a circular or they may have a rectangular kind of configuration, and what this will be a big pack of capillary tubes. So, each of these tubes then becomes one of the collecting element, and you really need to have a tiny diffusion path, so that by the time the fluid is traversing the length, the particle has already reached the wall. And similarly for this, you will have thin kinds of rectangular channels, if you will. So, these will be rectangular channels, and these are almost capillary tubes. So, you will have a pretty large amount of fraction of deposition. So, this is one of the things that we can stop our discussion with, and then just have some responses here before we move on to the next topic, where we will discuss both filtration as well as dry deposition. We had earlier in this idea of diffusion, particle diffusion, said that we can think or conceptualize of a particle path length for a diffusive particle, and said that we will compare it to the mean free path. And what had we arrived at? How much smaller was it, if you remember? So, it was of the order of factor of 10 smaller, right. So, it was of the order of, for 200 and for a 10 nanometer particle, 200 nanometer particle was the one which had the smallest diffusion path length, which is of the order of 10 nanometer. Now, a 10 nanometer particle, if you go back and look at that graph, it had a fairly high path length, but yet that path length was much smaller than that of the mean free path of gas molecules, or it was of the order of maybe half of that, right. So, you may have for the tiniest particles, and this of course is a 10 nanometer particle, you are looking at a particle path length of the order of, oh, what happened to my, right. So, we may be talking about 20 or 30 or something, while we were really talking about 65 or so for. And so, you are still smaller by a factor, a factor of 2 or so, right. So, that is one of the things that we wanted to look at, and oops, and coming to the other questions, see if anybody wants to take a little bit of an answer for any of these. So how does the diffusive particle reach a collector surface? Now let's make this into a collector, and we have a diffusive particle, and we have this streamline, and let us say the diffusive particle has a small diameter and the streamline is definitely much further away than dp by 2. How does the diffusive particle really reach the surface of the collector? Yes, so it is actually diffusing, but in a perpendicular direction to the direction of flow, right, is what we recognize. So simple, and this of course we already answered in class, that a thinner or finer element collects particles more efficiently because the streamline is already a lot closer to the surface. And so how does the boundary condition change? We change the boundary condition by saying that the particle concentration then goes to 0 by the time you are dp by 2 away from the surface, while in the other case the particle concentration goes to 0 only when you are right at the surface, right. So that was sort of the conceptual thing, and then we can move on. So this is what we had for diffusion and interception in terms of, so far what we had looked at in terms of low Reynolds number deposition and the deposition from pipes. Now let's take a look at filtration of particles and then move on to dry deposition, where we will actually look at high Reynolds number deposition, right. So why do we want to look at filtration? Filtration has huge applications. Whether you're talking about measurement of particles, whether you're talking about particles that need to be collected, you're talking about power plants, cement industry, nuclear plants, you're talking about controlling particles in clean rooms, in the manufacture of microelectronics, etc. And some of the most recent applications, of course, it's being conceptualized also for other applications in the atmosphere, as we'll look at. So lots and lots of applications, important to look at it. Now filter development, this is just to tell you some kind of history that we, and this is actually a very important field even today. As you all found, as soon as COVID hit, everybody was trying to manufacture N99 filters, right? And so it has these wide applications, and what I was telling you about some of the recent applications, and so we even have what are called smog towers, which is now an application. This is being shown in China, but some have been designed. In fact, Dr. Maya was one of the originators of a design in India, and the idea is to use electrically assisted filtration, and in a way to at least clean a section of the atmosphere close to the smog tower. Until we have effectively really controlled air pollution at the source, we have to find a way to manage it, right? And so that was where one of the new applications is. And what do filters look like? So we were talking about fiber mats, and fiber mats essentially have fibers that are pressed to each other, they are not woven, and so we have fiber mats that are essentially a bunch of fibers, and even though we said this one looks pretty packed, but we said that you have solids fractions smaller than 10%, 5%, etc., right? Then you have filters. The typical type of filters that people put into the N99 masks, etc., was some kind of foams. So they were polyurethane foams or some other kind of foams, and we manufacture foams for various applications, and those are being shown here in B. And C, these are used either with foam processes or with gel, what are called sol gel processes, where you precipitate things and then make them form some kind of a framework. But the very, very interesting one is the one which is right here, which is called a polycarbonate filter, and it was made for very, very low particle concentrations, where you also wanted to be very exact in the cutoff diameters that you collected. And so it took a polycarbonate sheet, and actually it is manufactured in a nuclear reactor. You have to bombard it with neutrons and then etch it for an exact period of time, which is why you have such clear pore sizes over here that look almost identical to each other. And one of the things, we just finished talking about diffusion batteries. I believe this has been modeled by somebody as a set of pores with diffusion happening in them, though the general understanding is that a large amount of the collection happens in the front, near the front face of the filter, but depending on the particle sizes. So here, this is more just information that you have fiber filters, membrane filters, capillary pore filters, etc., to give you a general engineering idea. And of course, you must already be thinking, how are we then going to account for two things, which is the fact that you don't have a single element anymore, and that's just coming up. This is something that you have seen in your theory regarding diffusion and interception. And we go on to the fact that you now have to account for the flow within the matrix of the filter, which has a solids fraction. So let us go ahead and, before putting this up, give you a very simple derivation of how we can conceptualize this and where that 1 minus alpha comes from. So we can just be conceptualizing this as a one-dimensional sort of system, where yes, we have a certain height and a certain W, but that height and the W are constant, and this is the filter bed where we have the fluid flowing in this direction, approaching the filter. I mean, it looks very thick, but really what it will be is, the way it will be macroscopically is it will be quite thin, but we are looking at it to see what's happening inside the filter bed. And we say that you have a certain number concentration N1, you have a certain velocity here, u infinity, whatever, and somewhere at a distance z, you are looking at a slice here dz, right? And you want to write a particle balance over here, right? So you will say that my velocity is u, I can have the hw here, and I will basically be taking it out from both sides of the equation, but I have a change in number concentration, right? And that's going to be a negative change, in that there's some deposition of the particles within that slice. What happened to this velocity when it came in here if what we have is a solids fraction alpha? So solids fraction is something like, so your porosity will be a 1 minus alpha, right? So in that volume, alpha is occupied by the solids and 1 minus alpha is the space that you have. So your velocity has to accommodate within the 1 minus alpha space, right? And so the velocity will go up, right? Alpha is going to be a small number and the velocity is going to go up, and this is what you have. And by the time that n1 reached here, it became an n, and so you have the velocity in the bed. Let's say you have a number per meter cubed of particles, and then you want to say in this slice, in delta z, what is the number of fibers? In dz, right? So imagine it as a h times w times dz is the total volume, right? Alpha is going to be the solids fraction. We are getting rid of the hw, so alpha dz is the amount of solid in terms of volume that's there in that slice, and each fiber is then occupying what sort of fraction in terms of its cross section. It's right, this is a fiber diameter, cylinder diameter. We're back to our collector, right? So this is the numbers of fibers. And then we had talked about the fact that we can conceptualize each fiber having a single fiber efficiency and cleaning up a certain length of the fluid flowing past, cleaning it completely free of particles, right? So what is that length, or you know, you want to say, maybe you want to call it height swept free, swept clean of particles, and we said that that is going to be some kind of a dc times an eta r, right? So this is what you have. And last time we'd had this interesting discussion about whether your eta r dc can actually be larger than dc, or and so on and so forth. And yes, for a single element that could be true based on how efficient a collector it is. So given this as the framework, we can go ahead and just integrate it. N1 to N2, which is an concentration is going to be 4 and we'll say that we're going, and this is called the bed depth, even though it's given the it's how thick your filter is, and it's going to be a very small bed depth. It's going to be a few millimeters, but you have fibers of a few micrometers, right? So you already have a factor of 10 to the 3 in terms of dimension between the fiber and the filter thickness, right? So now that you have this, you can go ahead and get yourself a bed efficiency. Now this bed efficiency, so we had said eta r could actually, can even be greater than 1 or it can be less than 1, right? Now this bed efficiency is a 1 minus n2 by n1 or n1 minus n2 by n1. And this bed efficiency is 100% always going to be less than 1, right? You've collected some of the particles, you haven't collected all of them, right? So when we're talking about bed efficiency, we have to make sure this is what we have, and if you go ahead and do the algebra, 1 minus exponential of minus 4 eta r. This is what we end up with the expression. expression, and you can see that there is that, here we're talking about the single element, and this is the bed. So, in the single element 1 minus alpha is in a different place, and what you have is the hydrodynamic factor has some dependence basically on alpha, and these are all, which is the solids fraction, and these are all calculated or determined experimentally, right? And yet you find that you have your Peclet to the minus 2/3 in the diffusion term, which is what you look for. Whenever you see a Peclet to the minus 2/3, you know the mechanism is a diffusive deposition. Whenever you see some R dependence, R square dependence, where R is interception parameter dP by dC, you know that you're talking about an interception mechanism, right? And once you get into impaction, you've got Stokes number coming in, right? So, your theory then gets put into expressions that are useful for any kind of design, right? And we can look at more. So, here you can see that single fiber efficiency, and see here you are seeing single fiber efficiency going greater than 1 only for large particles, right? But that is because this is a fiber diameter of 4 micron. When you go to much finer fiber diameters, you will see eta r also going greater than 1 on that side by diffusion, right? This 4 micron is not nearly a small enough fiber diameter to start seeing that effect. And also at a particular phase velocity of 15 centimeter per second. You can understand that if you had much smaller phase velocities, the fluid will have much more time within the filter bed for that diffusion to happen, right? And so, either you go to much smaller fibers, or you give it more time, then your eta r on the other side can go down. This is what we just finished deriving on the board, and so you have it, yeah.
How sensitive are these filters to the wall properties of the particular bed? As in, if its roughness changes, how will the position change? Must be very sensitive.
We'll come see here. The filter is nothing but a bed of fibers, or it is a spongy bed that has some tortuosity. It's not a straight through, but it has the fluid going in this way. There is, sort of here it's basically assumed that there isn't any roughness element, within either on the top of the cylinder, right? But we will come to that when we're talking about high Reynolds number deposition from the atmosphere, right? Their roughness lengths 100% will come into consideration. Here it's sort of, there isn't a sort of, yes, there is a surface, and most of the time we have used inviscid fluid approximations also, so we're not getting into roughness lengths and those kind of things even when you're talking about the deposition surface, right? And when we come to the bed efficiency, here you can see that very clearly the scale ends at 1, that you can have the highest efficiencies for both the smallest particles and the largest particles. So, this efficiency window, and we've talked about interception, really is the only pure interception is the only mechanism that is operating for that 200 to 300 nanometer particle. It's neither diffusive enough nor is it inertial enough, right. So, the particle itself is not able to do anything. It has to rely on the fluid to bring it to the collector, otherwise it does not get collected. So, it is really sort of a particle that does not have any ability to arrive at a collector by itself, right. So, that is sort of this idea of the minimum deposition efficiency corresponding to those particles. And as we have it, they will escape collection devices, they will penetrate the deep lung, and they will interact the most with radiation, those sizes. And so, we really have this idea that they are the hardest to collect, and in order to make them collectible, people have tried various things. In the second half, Dr. Maya will cover coagulation, and some of the things that have been tried is within collection devices to either have acoustic coagulation to grow particles out of that size range, even as the fluid is flowing through a collection device, right. So, I think that is pretty much it. There is two other things, which is this dp min, which is the particle size that is collected with the minimum of efficiency, most penetrating particle size, and you can get that as a function of phase velocity, as a function of solids fraction, and so on. But you can see that yeah, for many cases it's of the order of your 0.1, 0.2, 0.3 sort of diameter, if you look at some of the lowest curves over there. Yeah, and so what is these are all sort of semi-empirical types of things, and then for most engineers you also have to calculate the pressure drop because you have to provide and so on. So, I think we leave it there. There is some more information for you. I do not think there is anyone here who is interested in filtration as a practice, except for maybe if Hitesh was here, he might have been interested, but otherwise here I do not think there is too many people who are thinking about filtration in terms of an engineering application. I think the one question I want you all to think about is this: why do dp and u not appear in the filtration bed efficiency equation? Does it mean that neither the phase velocity nor the particle diameter affects this?
Since it's efficiency, it gets cancelled.
Huh?
Since it is efficiency.
No. We showed that the efficiency then depends on, of course, it so strongly depends on particle diameter, right? So, why don't I have a dp here and why don't I have a u here? Where did it go? Yes? Yes, it's all embedded inside this eta. So, everything including U, dp and various other fluid related properties, everything, they are all embedded inside the eta, right. So, it is just a question of asking a question in a confusing way that then gives professors a chance to challenge students. Okay, right. So, now we are done with this and we will move on to the next topic. Yeah, I think we can probably get through dry deposition. Here too, we'll take a little bit of time to develop theory and then go on to the slides. So, atmospheric dry deposition, and we're basically saying that it's important, and you have this idea of a deposition velocity in meter per second. And if you remember, for here we are going to talk about high Reynolds number turbulent diffusion case, and so we'll put up the sort of brief derivation for it. But you remember that Kav, we had in the other case as well, we had said that there is something called the Kav dP or Rp by d, right, and said this is something like a transfer rate meter per second, and you can think of it as a rate of particle transfer. And then we had gone ahead and put up this idea that how much is the fluid, how many particles are getting swept out and how many are getting transferred to the surface by diffusion, and this can be thought of as a rate. This is nothing but your deposition velocity. Dry deposition velocity for people who come from the atmospheric side of things. So, let us put up sort of the derivation like we did the last time. We have the same cylinder, we have everything else except that now this is going to be diffusion and interception at high Reynolds number, right. And maybe I can give you a little bit of a conceptual idea. So, you have the Earth's surface and you can really be thinking of, whatever it is on whatever scale, whether you're talking about gravel or whether you're talking about buildings, you have these roughness elements that are there. And so, you have Earth's surface and you have roughness elements. And these are called bluff bodies. And by bluff body, we're basically talking about the fact that you have an irregularly shaped body that disturbs the fluid flow in such a way that it really causes turbulence, and because of that, there is the fluid separates from the body, and therefore you end up having massive turbulent wakes on the other side and so on and so forth, right. But really you are thinking about what is the deposition on the front face. Now, why am I showing it at the tip is that all of us know that by the time we are moving close to the surface, the wall law starts kicking in, and so your fluid velocities are going to slow down drastically. So, where is the collection happening? The collection is really happening at the free tips of these roughness elements. So, that is sort of the way of thinking about it, right. And again, we will put up the derivation for a right cylinder, but now you are thinking of the cylinder being sort of vertically oriented, and you are saying it's vertically oriented over here, it's having the fluid flowing around it, and I am really going to consider a very short length of the cylinder before the velocity slows down as being the sort of length that is doing the collecting. But notice of course that it is the diameter of the cylinder which is still going to be the characteristic length, right. The characteristic length, and by the way this is a cylinder, but it could very well be a blade of grass, and you could have, you know, the width of a blade of grass which is of the order of 5 mm or 2 mm or something like that being the characteristic length, right. So, this is sort of the physical picture that we have with dry deposition to turbulent dry deposition to bluff bodies. But coming back to a cylinder, and exactly the same thing that we've done before, and what we're saying here is that, you know, this is your RC and you have the cylinder now is going into the board, but then it was standing up with the free end in the atmosphere, and we have the same convective diffusion equation. Okay. Now, so a lot of it comes from fluid mechanics, so we're just going to just take it as such, right. So, we say high Reynolds number in viscid flow and close to the stagnation point. And we're saying the same things here. We have a velocity boundary layer, we have a concentration, thin concentration boundary layer which forms within that velocity boundary layer, and so on and so forth. Now, the velocity fields are taken directly from, so the references to Schlichting and boundary layer flow, and basically you're saying that u and v become some function, of course, of x, y, but also this body parameter of the fluid and nu, which is kinematic viscosity. And so this is equal to mu by rho. And what is this omega? This omega is b u infinity by RC. And you recall that this body parameter was 2 for a cylinder, 3 for a sphere, the same body parameter that we had invoked when we had talked about Stokes number and critical Stokes number, right. So, this u and v can be written in terms of this, and we now get a new dimensionless group. Of course, we recognize that d, the particle diameter divided by the thickness of the concentration boundary layer that we had talked about earlier, right, delta, right, where the diameter of the particle is much smaller than the thickness of the boundary layer. What mechanism do we expect? It's diffusion controlled. The particle is very small, it has to itself get through the boundary layer, where dP by delta C is greater than 1, it's interception controlled, right. And all we will say over here is that we have a dimensionless group X. You know, just like last time we had a dimensionless group which was R A Peclet to the 1/3, that fell out. Here we have a new dimensionless group which is R Peclet to the 1/3, and here we have a Reynolds to the 1/6. So, that Reynolds was stuck inside the A last time, and we said it doesn't vary much, it's almost a constant, but that's not the case here. So here there's an explicit dependence high Reynolds number case, and we end up with a Reynolds to the 1/6, right? And in fact, we have exactly the same solution method. So I wanted to put that back on this side. So we, do our non-dimensionalizing once again in the x direction with respect to the cylinder characteristic length, in the y direction with respect to the particle characteristic length, Rp, just like we did last time, and N1 is n by n infinity with the particular boundary conditions same as last time, y1 far away tending to infinity, we have n1 is equal to 1, n goes to n infinity, y1 equal to 0 at the surface equal to 0, right? So here, because n1 is being defined as 1 radius away, y1 is being defined in terms of 1 radius away, right? So, and what is the solution to this? The solution to this is going to give us some concentration field as a function of x1, y1 and this big X, right? That's what we end up. When we non-dimensionalize the equation, you can write this equation where you're putting the u's, v's, etc. in terms of that capital X, right, which is your non-dimensional parameter. There are explicit expressions for this, right? So basically you'll go back and non-dimensionalize this whole equation and then take it, but a lot of it comes directly from fluid mechanics in terms of the form of the u and the v that you will plug in, right? So after that we get this, and what had we done earlier, we'll do the same thing. We had said that I want to have a flux at y1 equal to 0. I'm going to say what is that flux to the surface, and I'm going to integrate it from over the front face, and then I'm going to get the solution, right? So I'm sorry, at y1 equal to 1, right? And then I'm going to get the solution, right? So made a mistake here, right? So now that the method is the same, I'm just going to go ahead and put up the solution, and the solution looks like this. It is equal to x in the diffusion limit and is equal to x cubed in the interception limit. Right? And so we can get a and this is now in terms of a Peclet to the 1/3, etc., etc. And what had we done with this Kavg? We said, okay, let's now think of it as a single fiber, and let's go ahead and do the flow analogy and the mass transfer analogy, and that's how we had got a Peclet to the -2/3, right? So you go ahead and do the same sort of thing, and what we end up with is this. So we end up with removal efficiency, single element removal efficiency for cylinders and for spheres, right? And what does the first term look like? It has a Peclet to the minus 2/3. So, the first term in each case is a diffusion term. What does the second term look like? It has an R square, right? So, it looks like an interception term. Here you have the Reynolds number explicitly appearing in it in the turbulent case, right. So, this is what we finally get. This was derived by earlier parts of it, Fernandez de la Mora and Friedlander, and then this particular version by Richard Parnas and Friedlander, 1984 paper. And yeah, so does reality agree with any of this theory? And this is a very interesting graph, and I want you to look at the y and the x axis on these, and I'm going to write those down for you to understand what's being plotted. So, what is being plotted is some sort of a single, if you would, collector efficiency of removal from wind tunnel experiments. So, wind tunnel experiments in which they simply used to put, like your artificial grass kind of material at the bottom and flow. I've actually been around such experiments being done in our lab during my PhD days by somebody else. And you flow the fluid through it, and you measure the particle concentrations upwind of it and downwind, at the start of the experiment and at the end of the experiment, and you end up with the removal efficiency. Now, what is on the y-axis over there says capital Y, and there is an AP, which is nothing but a particle radius, what we were calling RP, right. So, all right. And then there is another term here which says Vd minus Cs, and there is a D, which is diffusion. So, I will write this as an Rp and a particle diffusion coefficient. Now, this deposition velocity, we said it's equivalent to a Kavg. What are they removing from it? They are removing a terminal settling velocity from it, just to make sure that they're keeping the interception idea and removing any gravitational settling, right. So, this whole thing over here is nothing but a Kavg. So, and that's what you have on this side of your equation, right. So, that's what they've plotted on the y-axis. And what is there on the x-axis? I told you sometimes it's called a pi, sometimes it's called an x, etc. It's nothing but our a non-dimensional parameter over there. But what is it in terms of? R Reynolds to the half, Schmidt to the 1/3. And what is the Schmidt number? A Schmidt number is equal to Peclet divided by Reynolds, right. So, you can just go ahead and, so it's, I'm sorry. Yeah, a Schmidt number is a Peclet divided by Reynolds, and so then you end up with an R Peclet to the 1/3, and of course the Reynolds becomes a half minus a 1/3, which becomes a 1/6. So, this is nothing but the form of the x that we had. So, on a log plot, and 8-kin nuclei, etc., and much tinier even, what are really this lead-212 is a certain lead isotope, etc., which are really molecules that are floating around. That is what is in the lower part of the curve, and you can see that it is proportional to x, which is the diffusion limit, right? And the upper part of the curve is proportional to an x cubed or a pi cubed, as it's shown over there, which is your interception limit, right? So, even from very real world data, you are able to kind of tease out and see whether it agrees with theory or not. So, I mean, for that it's very important then to have a good grasp of where that theory came from and how you should plot it. See, today is the day of course of data analytics. We don't want always to be asking AI to give us something from data. In fact, it's important for us to apply maybe our natural intelligence rather than going to artificial intelligence before that, and try then to pull out some theoretical behavior before asking an AI to give us relationships between variables and then not know what to do with that, right? So, this was natural intelligence being applied. And okay, so after this what we will talk about in deposition is related to the real world. Okay, this is where there is an idea that it goes back to theory. This is what, and particularly the atmospheric people will appreciate it as we go on, which is how do we apply this kind of neat theory in the real world, right? So, in the real world we have this idea that I have a deposition velocity, which is nothing but that k-av, and we've gone ahead and we've related it theoretically and so on and so forth. But I have a deposition velocity which has the units of meter per second, right? And typically what can I measure? Typically what I can measure is a flux in terms of depositing species, in terms of some integrated variable that can be measured over a period of time, right? And so then the deposition velocity into a surface layer concentration is what is called the deposition flux. And in this particular case, if you are talking about particle numbers, right, then you have a flux. If this is going to be a number per meter cubed and this is a meter per second, then you will have a number per meter square per second is your deposition flux, which then gets converted depending on whatever you are talking about to mass units and so on and so forth, depending on whether the particle contains black carbon or sulfate or whatever it is whose flux you want then to measure. Now, more or less I think we will use the slides because it's pretty much the same material then that has to be kind of written on the board. That this is conceptualized as a resistances in series model, right? And where are the resistances in series coming from? The first resistance is aerodynamic resistance, and it's aerodynamic resistance, which is basically saying that somehow the atmosphere has to bring it to some surface, and here you may be talking about leaves, you may be talking about canopies, you may be talking about grasses, you may be talking about just the surface of the earth, right? So whatever it is, the first is somehow the atmosphere has to bring it to the surface. The second one is what is called, and this is called the quasi-laminar layer. Why is it not, just called a, laminar boundary layer, as we call it? They call it quasi-laminar and all by basically recognizing, and this is sometimes called quasi-laminar sublayer. Now, the reason why it's called this is that, while you have the wind flowing over it, you might actually have more than one layer forming and so on and so forth, and that kind of general idea, that there is some part of the fluid that essentially somehow is stagnant close to the surface, and it is that thin layer through which the particle has to somehow transmit itself, right? Whether it is doing that by diffusion or by interception or by impaction, as the case may be. So that is where this quasi-laminar, and so this RB is really the one of our interest, and RC is what is called surface resistance, canopy resistance. So canopy, because you may be thinking about things depositing to forests and so on, etc. And this becomes really important for gases, right? This aerodynamic layer resistance in its simplest form for what is called a neutral atmosphere. For a neutral atmosphere, this takes the form of the logarithmic wall law that we're all used to. But really this course is more about what goes into this sublayer. So we can just kind of quickly show you that you have this idea that you have the that wall law appearing in the second case, right, for aerodynamic, where you have your friction velocity, you have the von Karman constant, and that is your roughness length, right? And your roughness length can be, if you're talking about gravel and short grasses and so on and so forth, your roughness lengths can be of the orders of millimeters to centimeters. If you're talking about buildings and so on, you're talking about a different scale and so on, right? So wherever your roughness lengths are. And so by the time you come to RB is where, and this is the kind of thing that you people will all be seeing in your documentation of your climate model, right? And you will see something that says, now I have a RB, I have it in terms of a given empirical constant, the friction velocity in the atmosphere, and then I have an efficiency, and that B over there is Brownian diffusion, okay? The IM is an impaction and an IN is an interception, right? So we're back to particle deposition mechanisms, and what do you see? You see your EB being Schmidt to the minus gamma, and it says this gamma is anywhere from half to 1/3, and Schmidt is a Peclet by Reynolds, so you've gotten back to your Peclet to the minus 1/3, right? But nobody, you can read thousands of pages of atmospheric science books and atmospheric physics and chemistry books, including Seinfeld and Pandis. They'll tell you a lot of other insights, but they'll just throw this at you, and you have no idea where this very nasty looking equation came from, right? But now you know, okay? And, huh? Huh? Sorry, yes, half to 2/3. Yeah, so half to 2/3, and then you can see over here that this E of impaction has a certain Stokes number dependence, right? So you have your Stokes number, and then the Stokes number can be defined based on whichever way it has to be defined over there. And if you go back and you look at, what each one of those are, you will end up with seeing that it is indeed in the Stokes number, because it's written in terms of a Vs, which is in terms of a rho p dp square, etc., and then because that Vs has a g in the numerator, it's divided by a g to get rid of that and so on and so forth, right? But really, if you put in everything, you'll end up with a Stokes number over there. And in the form that we know Stokes number, you will get it back, right? And then you have, this is the impaction, and then you have the interception one, and what you see is a dp by A is the characteristic length of the collector. So you have a dp by dc or dp by some characteristic length of the collector, which is an r, is nothing but proportional to r square, which is what your theory told you, right? So all of these get incorporated there, and then we have another term which says R1 is equal to exponential of minus Stokes number to the half, or it's a 1 by exponential of Stokes number to the half, which is basically saying that if Stokes number is getting very close to 0, then this thing is tending to 1. It says if I don't have a very inertial particle, it's going to somehow approach the surface and it's going to stick. And that's why that R1 then approaches 1. But as you start having Stokes numbers of any magnitudes, you're going to have a chance for it to bounce. And therefore, that R1 will become accordingly a value less than 1, right? So we had this idea of resistances in series, and then this quasi-laminar resistance is the one where the particles are essentially, the particle deposition mechanisms are coming into play. So that's really what this is about. They'll give you a lot more information, which of course is necessary for you to put into a model and to run a model, right? Which tells you, I want then to be able to specify these other parameters in the equation based on what real surface I'm looking at, and so on. And we can skip this, that surface resistance doesn't exist for particles, but it's really for gases, applies only really to gases. But this is again a very, very interesting compilation of real world data and theory. So this is deposition velocity versus particle diameter in real world measurements, right? So one of the things you all might have heard of is things called flux tower measurements and so on and so forth, where you measure velocities also at multiple heights from the Earth's surface and so on. And those kinds of measurements allow you to make accurate estimations of deposition, accurate estimations of how the velocity profile is varying really over there, and estimates of some of these. So here we have Some of these are controlled experiments, some of these are atmospheric experiments, and we have a large number of friction velocities, we have a large number of roughness lengths, and you correlate data and you end up with a Schmidt to the minus 2/3, which is a Peclet to the minus 2/3 on that side, and it says Vs, but Vs is then related to the dp square, right. So, on the other side. So, you have a certain behavior that is starting to resemble the and interception really will stop pretty much close to pure interception will pretty much stop close to here, and then after that inertial effects will come in. So, some Stokes number kind of dependence will come in, right. So, this is also this should be from Semel and so on. So, these curves are also attributed, I think the paper was that compiled it was Slin. And I think for people who do atmospheric work, just very quickly and then we'll stop, which is this is what if you go to Eckham documentation or you go to your climate model documentation, what you'll end up with is looking at all those equations once again being documented as existing within your model. And here I am showing you, since we ran in those days Eckham in our group, how we treated aerosols in multiple modes, nucleation, Aitken, accumulation and coarse mode, and this is giving you, they have some idea about where they will put soluble and insoluble species and treat the relative humidity effects differently, because you have to then have water associated with that mode and change the particle radius once it comes into equilibrium with the relative humidity. But yes, so we are looking at dry deposition velocities in meter per second. So, centimeter per second is going to be then of the order of 0.1 centimeter per second, 0.05 centimeter per second, etc. Deposition velocity is over here, and larger the deposition, the particle size, the larger the deposition velocity, and this is just showing you some results. We in those days used to publish some papers that are out there with deposition of black carbon dust, etc., to Himalayan surfaces, snow surfaces and so on and so forth. So, yeah, we can stop here, and this is for you all to consider, I think, more for yourselves. I didn't pay attention to what specific question to ask you out of these. Yeah, I think most of these you would know because we have just said them. Yeah, so if we neglect, deposition by gravitational effects, you may actually want to go back and calculate only diffusion and interception, right? And compare dust particles to black carbon particles for specific mechanisms to see what you will get, right? Yeah. Okay. Thank you.
I want to ask about this setting
That was only because they were trying to see whether it agrees with this theory, and this theory applies only to interception. right? Pure interception. It said diffusion controlling and interception controlling. In the real case, you will have a certain sedimentation also, but you want to remove that sedimentation effect to see whether you are able to get back the theoretical behavior related only to interception, which was the x cubed or pi cubed dependence. But yes, in real world, the sedimentation term will be the one that leads to the largest deposition for the very large particles, no question.
So, one more term I came across these papers, there is a term known as preferential clustering.
Preferential clustering.
Of these particles that are specific, I don't know, like I'm still.
Are you talking about dry deposition? I mean, are you talking about vortices and things like that? Because Professor Ravichandran has done some work which shows that in particular fields that have vortices and things like that, you will have a non-uniform particle number concentration. They'll end up being in particular locations within that field, and they will not be in other locations in that field, right? So, having some kind of a turbulent field can place the particles in a non-uniform concentration spatially. Maybe that's what they're talking about over there.
I came across this when I was doing some numerical simulations, and I found like particles are clustering at some locations.
Huh.
So I thought like whether it is a numerical issue or it is a realistic phenomenon.
Is it, was it a turbulent field? It was a turbulent field. Then it may be a real phenomenon. Particularly, you want to look, I mean, depending on whether they are small particles or large particles. We had said that, recirculation zones are traps for small particles. So, you might want to look at your flow field to see what is going on over there, right? The other thing over here, of course, is that while theory lies here, the actual measured deposition are factor of 10 or factor of 100 larger, right? And this remains to be answered. What typically, the hand wavy argument that's given is multiple element interference or something like that, and they'll just say that and leave it. But it's not a small factor, it's not a small factor. We're really looking at a factor of 10 or even a factor of 100 difference from the theory in terms of the actual deposition rates being much larger.
So, what kind of volume fractions are we talking about in this?
Oh, this particular one is not filtration. This particular one is wind tunnel experiments related to grasses and other surfaces. So, they will have certain roughness, known roughness lengths.
I mean, volume fraction of the suspended particles.
Oh, number concentrations will be very low. So, your volume fractions, as we had said, even if you have the largest mass concentrations, your volume fractions were of the order of 10 to the minus 6, right? Yeah, so 10 to the minus 6 or 10 to the minus 8 or whatever, right, is volume fractions. Volume fractions are very small. So, here is unknown physics for you all to work on. Okay, thank you.